The beginning of everything. As you can see from the subtitle, I'm trying to give a brief description of the origin and the very early history of the universe. This is something that looks like an animation, but actually it's a 3D atlas. In other words, we've mapped out the positions of galaxies in the sky and measured their distances, and using the position on the sky and their distance, we can work out where they are in three-dimensional space. And this is a computer-generated animation, not computer-generated in the sense of fanciful, but simply a three-dimensional representation of where galaxies actually are. So think of it more as a set of observations. So we know there are lots of galaxies out there, a huge number of galaxies, far more than is shown in this particular representation. But notice they're not uniformly distributed, they're grouped together, they're clumped. Sometimes we see galaxies that are lined up in so-called filaments, sometimes we see regions of space which look relatively empty. But certainly there's an awful lot out there. Many hundreds of billions of galaxies, possibly even trillions of galaxies. Each of those galaxies contain hundreds of billions of stars and a whole load of gas and a whole load of dust. So the question I'm asking this evening is, where did all that stuff come from? So we can take images like this. This is one particular image from the Hubble Space Telescope, a so-called deep field, where it's pointed to a patch of sky where there's nothing much in particular. Take a long exposure and you find that there are thousands upon thousands of galaxies. So in this particular image, essentially everything you can see is a galaxy, with the exception that there are perhaps one or two or maybe three stars in our own galaxy in this field of view. Everything else, all of the other thousands of smudges and dots, are galaxies, some close, some very distant. So I'm talking about where all this stuff came from, the creation of the universe. When did it happen? To the best of our knowledge, it happened about 13.8 billion years ago. How long did it take to make a universe? Well, it took about 3 minutes, substantially quicker than it'll take me to describe how it came to be. Where did it happen is a question that often arises, but you have to remember that we're talking about the creation of everything. Therefore, by definition, it happened everywhere. It didn't occur at one point in space where we can say that's where it all began. And why did the universe evolve the way it did? Well, because of the laws of physics. And how do we know all this? Same answer. Because of the laws of physics. So in a sense, you can think of the laws of physics as being the rules of the game. If we want to understand why the universe looks the way it does, we can ask ourselves, what rules is it following? And those rules are the laws of physics. So we can sort of make an analogy and say, if we want to understand where the universe has come from and why it's evolved the way it does, well, we're asking, what are the rules of the game? If we were to take a snapshot like this of a game of chess, can we figure out what the rules are that allowed us to get to this particular state? We know that particular pieces on the chessboard can only move according to a set of rules. But can we figure out what their rules are simply from a snapshot like this? And the answer, I think, is no. From a single snapshot, we can't tell what the rules of the game are. And in a same way, if we take a single snapshot, for instance, of a galaxy, even a very clear snapshot taken with the Hubble Space Telescope, simply taking a snapshot of a galaxy doesn't tell us what the rules of the game are, doesn't tell us the laws of physics that allowed this galaxy to come into being. An alternative would be to say, instead of taking a snapshot, can we watch a game being played? Because if we could watch a game being played, as the pieces move, we could start to figure out what the rules of the game are. But we can't really do that with, for instance, looking at a galaxy, because things don't happen fast enough. If we were to come back in 1 million years and have a look at this galaxy again, it would look pretty much the same. It would take hundreds of millions of years for a galaxy to rotate once. So it might have rotated many times in its lifetime, but we haven't got the patience to stare at a galaxy and see how it changes with time. So it's the same sort of argument as, well, it would be nice to watch a video of a chess game being played, but we can't do that. But the alternative is, if we can't watch a game being played, can we take a snapshot not of one game of chess? Can we take a snapshot of 1 million games of chess all being played and all at different points in the game? Or can we perhaps take a snapshot of 1 billion games of chess? If we had enough information, then perhaps we could work out the rules, even if we couldn't watch each game being played, if we had enough snapshots. And it's the same idea with looking into the universe. A picture of one galaxy is not enough. We can't take a video because it's too time consuming. But we can take snapshots of huge numbers of galaxies. Here, only a few thousand, but in principle, we can image many thousands, hundreds of thousands, millions, tens of millions of galaxies. And because the speed of light is finite, some of these galaxies are close to us and we're seeing them as they were fairly recently. But some of these galaxies are very distant, billions of light years away, so light has taken billions of years to reach us. So in that sense, we're seeing the galaxies as they were billions of years ago. So even though it's a snapshot, it's actually a snapshot with multiple layers, if you want to think of it that way. If we can figure out how far away the galaxies are, then we can effectively say that's what galaxies looked like a long time ago, and this is what galaxies look like now. So we can get, not a movie, not a video, but we can get slices at different times. And here's an equivalent taken by the James Webb Space Telescope, which can see a little bit further than the Hubble Space Telescope. For reasons I'm not going to go into, the James Webb can see a little further back in time and hence can get an idea of what the earliest galaxies were up to. And that gives us more useful information about how the universe has evolved. But you might say, isn't this rather futile? Surely the rules of the game are so complicated. How can we possibly understand the rules that have produced, for instance, this, which is our local neighbourhood? This is not distant galaxies. This is just a few colourful nebulae and stars in our vicinity. This is only a few thousand light years away. But it just reminds us that the universe is very complex. So doesn't that mean that we haven't got any chance of understanding how it came to look like this? Well, if we use a mathematical analogy, we can present this, the Mandelbrot set, or at least a very small part of the Mandelbrot set. It's a mathematical collection of points. Here I'm representing it as a mathematical collection of coloured pixels. Each pixel in the Mandelbrot set, which is technically infinite, and we're just looking at a small section of it here, a few million pixels, each pixel is coloured according to a mathematical formula. And if we wanted to, we could zoom into this and we would see an infinite amount of detail. I'm not going to do so, but we could keep on zooming into more and more and more detail, and that detail would never repeat. Yes, there are certain motifs that you can see here which appear to be self-similar. Certain patterns seem to repeat, but actually they don't repeat. They're just similar to each other. In much the same way that our Milky Way contains 100 or more billion stars. None of those stars are identical. They may all look similar to each other, but none of them are identical. Similarly, every pattern of pixels you can see here might look similar to another pattern, but none of them ever repeat. So, how complex is the mathematical formula that allows us to create an infinite number of pixels of infinite complexity? and infinite detail? Well, the mathematical formula that allows us to construct the entirety of the Mandelbrot set is that. I'm not going to say how we do it, but that is the rule that we apply to generate every pixel in the Mandelbrot set. So just because something looks amazingly detailed and amazingly complex does not mean that the rules of the game are beyond our comprehension. And this is one of my favourite quotes from Einstein. Complexity and comprehensibility are two different things. The most incomprehensible thing about the world, and in this context treat that as the universe, the most incomprehensible thing about the universe is that it is comprehensible. And we can figure out what the rules of the game are. The flow of thought that we use goes something like this. For a while now, we've been observing the universe, and we've noticed that galaxies are all receding from each other, and all of them appear to be receding from us. And we come to the conclusion that the universe is expanding. And if the universe is expanding, we can say to ourselves, well, if it's expanding, we can wind the clock back and imagine that things used to be a lot closer together. We can also add our knowledge of how the universe is put together by doing experiments here on Earth, and also thinking about how things seem to behave. In particular, we can do particle physics experiments. So, for instance, the Large Hadron Collider in CERN, we can bang things together and smash atoms and think of what atoms are made of and get an idea of what the building blocks of matter are. We have to make some assumptions, though, if we want to make any progress with understanding the universe. We have to assume that the laws of physics in one place are the same as the laws of physics in another place. If that wasn't the case, then we would not be able to make any progress whatsoever. If the laws of physics in the United Kingdom were not the same as the laws of physics in Australia, then again we would have no chance of understanding anything. And we can extrapolate that and say, well, the laws of physics as we understand them here on Earth must be the same as the laws of physics in the Andromeda galaxy, or in any distant galaxy which we care to choose. If that isn't the case, if the laws of physics change from one place to another, then we can't possibly take anything we understand here and apply it anywhere else. And in a similar vein, we have to assume that the laws of physics as they apply now are the same as the laws of physics have been in the past and will be in the future. Again, we can't prove that's the case, but if that's not the case, we cannot understand anything. If the laws of physics we obtain today are different tomorrow, then anything we understand today won't apply tomorrow, and therefore we have no ability to understand. So we have to make those two assumptions. And we come to the conclusion, based on our observations, based on our experiments, and based on those assumptions, we come to the conclusion that the universe was created in a very hot, dense state 13.8 billion years ago. And ever since then, it's been expanding and very slowly cooling off. But the question I'm addressing really is, if the universe is currently full of galaxies, which are made of stars and gas and dust and maybe a few bits of other plus stuff as well, where did all this stuff come from? Where did all the matter that we see today come from in the first place? We can ask ourselves, if we think physics now has applied as far back as we want to go, well, just how far back in time do we think we can go back to the point of creation? How far before we have to say we are not altogether convinced that we believe that the laws of physics as we understand them today still hold? Can we go back to the first year of the 13.8 billion year history of the universe? Yes, no problem at all. Can we go back to the first day? Yes. Can we go back to the first hour? Yes. Can we go back to the first minute? Yes. Can we go back to the first second and still believe that the rules of physics, the rules of the game, still hold? Yes. Can we go back to the first millisecond? Yes. Can we go back to the first microsecond? Yes. Can we go back to the first nanosecond? Yes. Can we go back to the first picosecond? Probably not. There's a watershed, and a picosecond represents that watershed. Basically, before that first picosecond, we're not sure what actually happened. But from that picosecond, from that 1/1,000,000th of a second onwards, we think we're on relatively solid ground. In other words, we think we've got a good handle on what the universe has been doing ever since 1/1,000,000th of a second after what we call the Big Bang. In other words, in a sense, we don't know what the Big Bang was. We don't know what happened at t=0, but we do know what happened later, and we do know how the universe has evolved. So that was a rather large introduction to what it is I'm talking about this evening. I'm going to spend one slide just setting out a basic set of ideas that will help us understand the following slides, where we're going to look at a time sequence. What happened in the first fraction of a second? What happened in the first few seconds? What happened in the first few minutes? And then we'll change gear somewhat, otherwise we're going to be here for quite a while. We'll change gear and fast forward for the next 380,000 years, and there's a particular reason why we've chosen that number. And then again we'll change gear and fast forward the next 13.8 billion years up to the present day. So the first set of ideas that we need to establish for the rest of this to make any sort of sense. Some of these ideas you might already know, some of them you might not. So firstly, we are made of atoms. I hope that comes as no surprise to anybody. We are made of atoms, and so we have to ask ourselves, what are atoms made of? Atoms are not fundamental particles. They are made of smaller bits. An atom is a nucleus made up of some combination of charged particles that we call protons and neutral particles that we call neutrons. And there's a whole load of electrons buzzing around those nuclei. If we wanted to, if we applied enough energy, we could take an atom and we could separate it into a nucleus and a whole load of electrons. In other words, we could, if we wanted to, strip the electrons off an atom and just leave us with a positively charged nucleus. Electrons, to the best of our knowledge, are not made of anything. In other words, we can't take an electron and ask ourselves, if we were to cut it in half and look inside, what would we find? As far as we can tell, we can't cut an electron in half. It is not made of anything else. It is just an electron. Whereas a nucleus is not a fundamental particle. It has got something inside it. It is made of something else. Given enough energy, we can take a nucleus and we find that it's actually made of other things, and we just label those things protons and neutrons. These labels have come about because protons have a positive charge and neutrons are neutral. They don't have a positive or negative charge. Are protons and neutrons fundamental? No, it would appear that they are made of something else. Given enough energy, we can tell that protons are actually made of other particles, and we give those particles the rather odd name of quarks. And a proton is made of 3 quarks. Neutrons are also made of 3 quarks, but I'm just giving an idea of the hierarchy of structure here. So we have this sort of Russian doll. Given a whole collection of quarks, which we believe are fundamental, they are not made of anything else, they are just fundamental particles. Quarks can get together to make protons. Protons and neutrons can get together to make nuclei of atoms. Nuclei and electrons can get together to make atoms, and we know the rest. Atoms can make molecules, molecules can make us, and pretty much everything else we see in the world around us. But I've said that in order to split an atom or to split a nucleus or to look inside a proton, it takes energy. So there's an implied energy scale here in this Russian doll, from low energy at the top to higher energy at the bottom. But remember our observation of the universe and the fact that it's expanding and cooling, so it used to be hotter in the past. To a physicist, low energy means low temperature, because temperature is effectively just a measure of how much energy the various particles in the system have. So low energy is effectively low temperature, and high energy is high temperature, and the universe started hot and is cooling off. So there is a time direction to this diagram as well. Because we're hot at the bottom and cold at the top, time is running from the bottom upwards. So the universe was made from the bottom up. And what we mean is that because there is effectively an energy scale here, quarks can get together to make protons, but only when the universe is cold enough to allow that to happen. Because if the universe is really hot and those quarks have got a lot of energy, because it's a high temperature, effectively the proton falls to pieces. And we have to wait even later until the universe has cooled off some more before protons and neutrons can get together to make a nucleus. If we try and get protons and neutrons to make a nucleus when the universe is still too hot, there's so much energy there, the nucleus will fall apart. And similarly, we have to wait even later until the universe has cooled off even more before nuclei and electrons can get together to make atoms. Because if we try to do that before the universe has cooled off, the universe will have so much energy because the temperature will be so high that nuclei and electrons will have so much energy, atoms will shake themselves apart. So there's this sequence in which things are made, built from the bottom upwards. So let's start the time sequence and say, okay, what happened at the instant of t equals 0 when the universe was created? And of course, scientists must admit that we do not know. We cannot provide a definitive answer of what happened at t equals 0. We can only talk about what happened a fraction of a second after that. There are plenty of hypotheses. There are plenty of ideas as to what might have happened at t equals 0. For instance, we know about quantum theory or quantum mechanics, which allows you to borrow energy from nothing, which sounds really weird, and indeed it is really weird because quantum theory is weird. Quantum theory has been with us for 100 years or more, and so far nothing has proved quantum theory wrong. So if quantum theory allows you to borrow energy from nothing, perhaps that's what happened. There was a little fluctuation in which energy was borrowed from nothing, and that energy was used to make the universe. Now, I'm sure that sounds like a complete and utter cheat, and not everybody is happy with this explanation. I call it an explanation. It's not really an explanation. It's a hypothesis. But you could ask, according to our understanding of quantum theory, how much energy could you borrow? Well, according to our understanding, energy multiplied by time, in other words, how much energy you borrow multiplied by how long you borrow it for, that product of those two numbers has an upper limit. In other words, you can borrow a large amount of energy for a short time or vice versa. Bit like borrowing money from the bank. If you borrow a lot of money, you've got a lot of interest to pay back in a short time. If you borrow a small amount of money and you borrow it for a very long time, you might end up paying back the same amount of interest. So one question is, well, how much energy would you have to borrow to make a universe? Well, the rather odd answer is when you look into the universe and you say how much energy is there out there, there's a certain amount of energy because of all the matter that exists, and E equals mc squared gives us the exchange rate, if you like, between energy and matter. We add up all of the positive energy because of matter, and there's a whole load of gravitational energy, which is negative, and we add up all of the positive energy and all of the negative energy, and the answer seems to be, well, somewhere near 0. If the total energy of the universe is 0, then the length of time we have to pay back the loan of the energy we borrowed, well, maybe that's going to be an awful long time. Again, I'm not expecting you to agree with what I'm saying here. This is just conjecture, because we cannot prove anything about what was going on in the first picosecond. Let's fast forward from 0 to that particular point. 0.0000, you can count the zeros yourself. A very small length of time after t equals 0. The universe started from effectively nothing, and after this length of time has expanded until it's about the size of a golf ball. I'm talking about the observable universe. We don't know how big the universe is. But if we think about the observable universe, everything that we can currently see is inside a sphere of diameter 100 billion light years. But back at this particular point, everything was much closer together. Not billions of light years apart, but centimeters apart. Everything that we currently see in the observable universe was only a few centimeters apart. So that's why I liken it to a golf ball. And just like a golf ball has dimples in the surface, well, the early universe had dimples as well. Not dimples in the same sense, not dimples in the surface of this sphere, but small irregularities, small variations in temperature and pressure. And most importantly, small variations in density. Eventually, when the universe has expanded until it was much, 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 much bigger, those tiny variations in density eventually became the large-scale structures that we see in the universe today. In other words, those tiny variations in density ultimately gave rise to the galaxies and the clusters of galaxies that we see today. We're now going forward to 1 picosecond. This is the watershed where we say from this moment onwards, we've got a reasonable idea of what's going on. At 1 picosecond, the universe has now expanded from the size of a golf ball until something roughly the size of the solar system. Of course, the solar system doesn't exist yet, but just to give you an idea of the scale we're talking about. So in a tiny fraction of a second, the universe has expanded from a golf ball to something that's many light hours in diameter. So it's expanded much, 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 much faster than the speed of light. The universe is allowed to do this if it wants to. The temperature has fallen to approximately 10 to the power 15 Kelvin. And the energy of anything that's in the so-called soup of matter, because we've borrowed energy, we can make matter. The matter is a whole load of fundamental particles, so it's probably quarks and electrons and other exotic particles as well. I am not going to refer to them all. I'm simply going to say there's a soup of matter and antimatter particles that were generated. Let's just simply call it a quark soup. The energy of each of the constituents of this quark soup at a temperature of 10 to the 15 Kelvin, the energy of all of the particles is roughly speaking equal to the energy of the particles that we can accelerate in the Large Hadron Collider. In other words, the state of the universe at this particular point in time is something that we can effectively recreate in the laboratory, at least for a few particles. So if we want to test any ideas we've got of how these particles might behave, we can do experiments in the lab to verify whether our ideas are right or wrong. So from this point onwards, our ideas are testable, which is why from this point onwards, it's a theory rather than purely a hypothesis. A hypothesis is just a conjecture or an idea. A theory is an explanation which can be tested against experiments. And therefore the Big Bang Theory from this point onwards is a genuine theory. We can test our ideas in an accelerator here on Earth, and therefore from this 1 picosecond point onwards, we have a reasonably good idea of how the universe evolved. So prior to this point, conjecture. From this point onwards, we are on relatively solid ground. Now, we said we've borrowed energy. We're not going to worry too much about whether that's right or wrong, but essentially we seem to have borrowed some energy and are now able to convert that energy into matter. And energy and matter are continually exchanging back and forth. Now, whenever energy makes matter, it also makes antimatter as well. Every particle seems to have an antiparticle equivalent. In other words, we know about electrons. Every electron has an antiparticle called an anti-electron. And we know about particles like protons and neutrons, and all of those have antiparticle equivalents as well. To the best of our knowledge, energy made equal amounts of matter and antimatter. Now, I don't know, graphically speaking, how to represent energy, so I'm just going to represent it as a big capital E. So energy makes matter and antimatter, or if you prefer, particles and their antiparticles. Now, energy doesn't necessarily make a tangerine and an anti-tangerine, but the point of this graphic is it doesn't matter. Energy makes something and it's anti-something. It will probably generate electrons and anti-electrons. It will probably generate quarks and anti-quarks. The point is, it doesn't matter. Energy makes stuff and anti-stuff. And those particles and antiparticles will then annihilate and generate energy again. And that energy is available now to make something else. It doesn't have to make the same pair of particles and antiparticles. It could make something completely different. Probably not a hot dog and an anti-hot dog. It's much more likely to make a quark and an anti-quark, or an electron and an anti-electron. Again, it doesn't matter. It makes something and the antimatter equivalent of that something. Backwards and forwards, matter and energy, back and forth and back and forth. Somehow, via a mechanism that we really don't understand, matter gained a very small excess over antimatter. I've represented it here by saying a whole load of matter was created and a slightly different amount of antimatter. So here I'm representing matter and antimatter imbalance as if it was a 10% imbalance of matter over antimatter. In fact, the difference was absolutely tiny. The difference was not 1 part in 10, the difference was 1 part in a billion. But it's a very important imbalance because all of the matter and antimatter ultimately annihilated to produce energy. Energy generally in the form of radiation. So think of it as generating light, if you prefer. Matter and antimatter would generate light. But that little bit of matter left over on the right-hand side does not have any antimatter to annihilate with. So what happens to that matter? Well, it stays put. And basically, that means we end up in a universe which is full of light, because each of these capital E's represents a certain amount of energy in the form of light, and we have a little bit of matter left over. So we have light and everything else we can see in the observable universe is that little bit that was left over. That is everything. That's you, me, the Earth, the Sun, the solar system, the Milky Way, and every galaxy that we can see in the observable universe is that tiny amount of matter that was left over when it had no antimatter to annihilate with. So it's just as well an imbalance did occur. Otherwise, we would be in a universe, well, actually, we wouldn't. We would have a universe full of light and nothing else. Let's move forward in time to 1 millisecond after the instant of creation. Matter and antimatter are continuing to pop into and out of existence. Now, whenever quarks get together, which they will do once the universe has cooled off at this point, after a millisecond or so, quarks can now get together. I am not going to talk about the different types of quark and why I'm labeling them U and D. And I'm not going to talk about why we colour them red, green and blue. But whenever we have a combination of three quarks as indicated on the left, we call that combination a proton. And whenever three quarks get together and produce a combination as indicated on the right, we call that particular combination of quarks a neutron. Protons and neutrons are just the names we give to a bag of quarks like this or a bag of quarks like that. Because there is enough energy floating around, quarks can quite happily change into energy and then into another quark. So in other words, the particular combination of quarks that we call a proton can change into a different combination of quarks. In other words, protons can change into neutrons and neutrons can change into protons, because quarks can change into other quarks by making energy and then that energy making more quarks. So again, protons and neutrons back and forth and back and forth and back and forth. But now if we go to 1 second, the universe has expanded and cooled a little bit more. The universe is now cooled to about 1 billion Kelvin. That, I'm sure, sounds very hot. But we can calculate that when the universe is at that sort of temperature, it would be essentially too cold for protons and neutrons to readily change back and forth and back and forth. In other words, you need a certain amount of energy for that to happen. When the universe is too cold, protons and neutrons can't change back and forth readily. Now we know that protons are a little bit lighter than neutrons. How do we know that? Because we can measure it in the laboratory today. And to the best of our knowledge, a proton now is exactly the same as a proton billions of years ago, and indeed is the same as what a proton will be many billions of years from now. So if we know that protons are lighter than neutrons now, then we can deduce that protons were lighter than neutrons back in this point 1 second after the Big Bang. So I can represent that by assuming that we're talking about protons which are red objects and neutrons which are blue objects. So according to these scales, protons are lighter, and they're lighter by about 1 part in 1,000. And if we know roughly what the temperature is, and we know the mass difference of protons and neutrons, we can calculate that the universe will make more protons than neutrons, and it'll actually be the ratio of 3/4. I've taken a representative collection of 16 objects, and it turns out 12 of them would be protons and 4 of them would be neutrons. Why does the universe make more protons than neutrons if it's got a choice of making either of them? Well, if protons are lighter, well, you can either say nature always favours the lower energy, or if you prefer the lower mass, because essentially mass and energy are the same thing because we have an exchange rate between mass and energy, E equals mc squared. Another way of looking at it is protons are lighter, therefore they're easier to make. Therefore the universe makes more of them. So at this particular point, 1 second after the Big Bang, when the universe is 1 billion Kelvin in temperature, we have made a universe which is 3/4 protons and 1/4 neutrons. Now it doesn't stay quite like that for very long, because we know that after a few minutes, let's say about 1,000 seconds or so, we know that because neutrons are unstable, some of them will change into protons. Neutrons are heavier, and it is possible for heavy objects to decay or change into lighter objects. That's allowed according to our understanding of the way particles behave. And again, how do we know neutrons are unstable? Because we can measure them in the laboratory today. And if neutrons are unstable today, then they must have been unstable 13.8 billion years ago. So we can calculate that after a few minutes, some of those neutrons will have changed into protons. And so instead of 12 of one and 4 of the other, the ratio has changed because some of the blue have changed to red. Instead of 12 and 4, we now have 14 and 2 of our representative batch of 16 objects. The universe is now full of 14 protons for every 2 neutrons. After 100 or so seconds, the universe has cooled to only 100 million Kelvin. And at this point, the nuclei of atoms can form. In other words, before this point, the universe was too hot for protons and neutrons to get together. If they tried, they would shake themselves apart. But now the universe is cold enough for protons and neutrons to get together. And what they would really like to do is form the most stable structure they can, which turns out to be 2 protons bonded to 2 neutrons. A collection of 4 particles, 2 protons and 2 neutrons, is a very stable structure we find when we observe them today. So what actually happens is we find 2 protons and 2 neutrons get together, and they make what we call either an alpha particle, or we label it as, well, actually that's what the nucleus of helium is. Helium is an atom whose nucleus is made up of 2 protons and 2 neutrons. But of course, we only have in this particular graphic here 2 blues. So we can get 2 blues and 2 reds together to make this very stable structure. Great. But now we're left with 12 bachelors because they can't find any neutrons to pair up with because there are too many protons compared to the neutrons. So once the universe has made this very stable structure, which we call the nucleus of helium, we're left with a load of bachelors which are just lone protons, which we could label, if we wish, the nuclei of hydrogen atoms, because the nucleus of a hydrogen atom is just 1 lone proton. So after 2 or 3 minutes, the relative abundance of hydrogen and helium is now fixed. After this point, once we've gone past a few minutes, the universe is too cold for the ratio of protons to neutrons to change, and hence the ratio of hydrogen to helium to change. So the Big Bang Theory predicts that the universe should be full of, by mass, 3/4 hydrogen and 1/4 helium. When we look out into the universe, we see an awful lot of gas out there. What's the ratio of hydrogen to helium that we find in the observable universe? It is this: 3/4 hydrogen to 1/4 helium. Big Bang Theory predicts that ratio. It also predicts a tiny amount of other heavier elements, but let's not worry about that for the moment. The fact that Big Bang Theory can predict the correct ratio for how much hydrogen and helium there is in the universe is a good indicator that Big Bang Theory is correct. We're now going to fast forward from 3 minutes to 380,000 years. Sounds like a big jump, but there's a very specific reason for going to this point in time. Because up to this point, nothing of any interest happens, basically, for 1/3 of a million years. Yes, the universe continues to expand, and yes, the universe continues to cool down. But in terms of what is the gas doing, well, it's doing very little in particular. We still have a universe full of 3/4 hydrogen, 1/4 helium. But eventually, the universe will cool down until it reaches a temperature of about 3000 Kelvin. And it does that at this point, 380,000 years after the Big Bang. At this temperature, it is possible for a nucleus to hang on to some electrons, and so atoms can exist. Up to this point, nuclei have been floating around, positively charged nuclei, and negatively charged electrons have been floating around in this, what I've been calling a quark soup. Now we can call it a proton, neutron, electron soup if you wish. Up to this point, they've all been separate. But now it is possible for a positively charged nucleus, like an alpha particle or a proton, to hang on to the electron and make an atom. Make a neutrally charged atom. So up to this point, the universe has been ionized plasma. In other words, it's been separated positive and negative charge because the electrons have not been part of the atoms. But now, for the first time, we have atoms made up of positive and negative charge, so each atom is neutral. It's no longer a plasma of positive and negative charge. So from this point onwards, the universe becomes transparent. So up to this point, light has been trapped in the plasma because it keeps bouncing off the positive and negative charge in the plasma of the universe. But now the universe becomes transparent, so any light that existed at this point is now free to fly across the universe. What colour is the light if an object's at 3000 Kelvin? If you take an object and heat it up to more than 1000 Kelvin, it becomes red hot. If you take an object and heat it up to 3000 Kelvin, it becomes white hot. In other words, most of the light that was flying around the universe at this point was visible light. A little bit of UV, a little bit of infrared, but a lot of it was visible light. And because of the expansion of the universe, that visible light has been stretched. Because remember, this happened a long time ago. The universe now is 1,000 times bigger than the universe was at this point in time. So all of the light that existed then, the visible light, has been stretched. Its wavelength is now 1,000 times longer than it was. So if you take visible light with a wavelength of about a micron and stretch it 1,000-fold, what do you get? Well, the electromagnetic radiation with a wavelength 1,000 times longer than the wavelength of light is what we call microwaves. And that is why we see microwaves all over the sky. This is a map of cosmic microwave background. In other words, it's the entire sky unwrapped so that we can see it all. And microwaves are coming from all directions, and we interpret that as being, if you like, the echo of the Big Bang. It is the light that was released when the universe became transparent, and ever since that point it's been flying across the universe, and we see it as the microwave background. It's relatively uniform, it's coming from all directions, but there is a little bit of variation. And here we've exaggerated that radiation, that variation in intensity of the microwaves by showing those bits that are a little bit brighter in red and those bits that are a little bit less bright in blue. And this small variation in brightness of the microwave background is essentially the same as the dimples in the golf ball. Small variations in temperature and density that existed in the early universe have imprinted themselves on the cosmic microwave background. And that's why observations of the cosmic microwave background, sending satellites up above the Earth so we get a good view of what this so-called CMB actually looks like, and in particular, not its average intensity, but those small variations from being perfectly smooth. Those small variations are effectively telling us about the dimples in the golf ball and hence telling us about the early universe. That's why studying the cosmic microwave background has proved so important in the last few decades. We can get an idea of how the dimples in the golf ball not only give rise to the cosmic microwave background, but in particular give rise to what we see in the observable universe. How is it that these small variations in density ultimately give rise to the galaxies that we can see? We can't watch the universe evolve, but we can run simulations, assuming we've got the rules of the game right, assuming we understand the laws of physics. We can say, let's start with a chunk of the universe, not the whole universe, but let's take a cube which is full of stuff, and let's put a little bit of variation in there. Let's not fill it uniformly with matter. Let's put in a small variation of density and temperature, which we think existed in the early universe. And basically, let's run this simulation and let gravity do its stuff. What we find is that gravity makes the denser regions even more dense, and the less dense regions open up into voids. Let's watch this simulation run. If you want to do it for yourself, the web address at the bottom there tells you where you can find more of these simulations. So we run the simulation. The bits that were more dense become even more dense, and the bright regions here indicate higher and higher and higher density. So notice that we don't get a uniform spread of matter, it clumps. And we get some regions which are much more clumpy than others. These regions are superclusters and clusters of galaxies. Each bright point represents a concentration of matter. Notice that it's not uniform, it is clumpy, and some of these clumps seem to line up on these filaments, much as we saw in the 3D fly-through of the observable universe. And we also see some regions which appear to be less dense. Some regions seem to be almost empty of galaxies in the simulation, and that is indeed what we find when we look out into the universe. Some voids appear to be almost empty of galaxies, and other regions appear to be very heavily populated. So the fact that these simulations give us an idea of what the universe looks like now, again gives us some assurance that we think we've got the rules of the game right. When we look at what's going on in our immediate neighbourhood, here's a two-dimensional representation of where galaxies are in our immediate neighbourhood. There's the Milky Way galaxy near the centre, the Andromeda galaxy, one of the biggest galaxies that's fairly close to us. There are dozens, if not hundreds, of smaller galaxies, small satellite galaxies around us. If we zoom out from this scale and see what's happening on a larger scale, well, all of the so-called local group, all of the galaxies close to us are in the center here, and we notice that there are other clusters and superclusters of galaxies not far away from us. But again, they're not uniformly distributed. They appear to be, as it were, on a line running from bottom left to top right in this particular representation. And if we zoom out further in terms of this galactic map, again, we see that we're near the center. Here's the Virgo supercluster. There's other superclusters. And again, we can see these various structures seem to follow a filamentary type web structure. And again, we notice that, for instance, over here on the right, the so-called Bouteille's void, there are some regions which appear to be empty of galaxies. So the fact that we're seeing this large-scale structure to the universe in terms of where the galaxies are is a reflection of the dimples in the golf ball. The fact that the early universe had small variations of density and temperature and pressure, which ultimately, through the force of gravity, collapsed these density variations until we get the structures that we see today. If we go forward to the present day, 13.8 billion years after the Big Bang, well, we could say that now that we've got a good handle on where the hydrogen comes from, if we say that yes, we understand that the hydrogen was made in the first 3 minutes, then we know that hydrogen is used to make stars. So if we understand where the hydrogen comes from, then in essence, we can understand where all of the stars in the galaxies come from. And also the fact that around stars will be planets, and on those planets there will be trees and mountains and snowflakes and rainbows and cats. And we can understand all of those. Well, okay, maybe not cats. I don't think we'll ever understand cats. But we can at least understand essentially everything as long as we can understand where the hydrogen comes from. So Big Bang theory tells us about the hydrogen, and yes, we still have some details of cosmic evolution to work out, but if we start with enough hydrogen and process that hydrogen through stars and make helium and carbon and nitrogen and oxygen and calcium and phosphorus and iron and all the elements that make us us, then perhaps we can understand pretty much everything. Well, not quite everything, but before I finish, let me just recap in a visual way what I've been talking about. So the universe came into existence at a time t equals 0 via a process we don't understand. We think it expanded until it was about the size of a golf ball in a ridiculously short time of 10 to the minus 35 seconds or so. And there were small variations in that small golf ball, and those density variations produced particles. The density variations ultimately produced large-scale structures in the universe, but the energy we borrowed within that golf ball, in other words, the golf ball contains a whole load of particles because we borrowed energy and made quarks and antiquarks, and we made electrons and anti-electrons, etc. So the golf ball contains a whole load of particles and antiparticles. In the very early universe, it was too hot for them to get together, but eventually it was possible, after a few seconds or so, for the quarks to get together to make protons and neutrons. And after a few minutes, those protons and neutrons can get together to make helium. Any protons left over are what we now call hydrogen. And if we wait until 380,000 years later, eventually those nuclei can hang on to some electrons, which are also floating around in the soup, and make neutral atoms, at which point the light is released. And that's the light we see in the cosmic microwave background. The dimples in the very early cosmic golf ball, gravity took a hold. If you give it enough time, gravity will take a hold of those dimples and form the structures that we see today, stars and galaxies. It took a while for the first stars to actually switch on. We're not sure exactly how long that took. From the point at which the cosmic microwave background was created, 380,000 years, we're not sure how many million years it took for the first stars to be born. One of the jobs of the James Webb Space Telescope is to look back in time as far as possible to see what is the evidence for the first galaxies and the first stars forming. Was it a few 100 million years after the Big Bang? That's the question we're currently trying to answer. So the Dark Ages simply refer to the time before the first stars lit up the universe. And of course now we have a good idea of what's going on in terms of we can see lots of galaxies, some close, some very distant, and we know that there are many billions, if not trillions, of galaxies in the observable universe. But I've skated over some of the problems. We do have a reasonable understanding of how the universe has evolved, but there are some absolutely key things which we still do not understand. The jigsaw is not yet complete. One of the big questions is, why did matter win over antimatter? It seems that it must have done so because we are here and the Milky Way is here, and every galaxy that we can see in the observable universe appears to be made of matter, not antimatter. So an asymmetry was in existence in the very early universe. But what caused the asymmetry in the first place? We can characterize the asymmetry by doing particle physics experiments and looking at the difference between matter and antimatter. But that doesn't necessarily tell us why it occurred in the first place. And we know there's stuff out there that we can't see. We know that there is so-called dark matter. When we look at how stars are rotating around galaxies, around the centers of galaxies, stars appear to be rotating at speeds that are much higher than we would expect, based simply on how many stars there are in the galaxy. It's as if the galaxy contains far more mass than we can actually account for by counting all the stars and looking at all the gas and looking at all the dust. In other words, everything we can see doesn't account for everything that's there. And the other big mystery that's cropped up in the last quarter century is dark energy. It would appear that not only is the universe expanding, which we've known for about a century or so, But it looks like observations over the last few decades have told us that the expansion is not slowing down as we might expect if gravity is pulling on everything. The expansion isn't slowing down, the expansion is speeding up. And this came as quite a surprise when it was first observed. And we, as yet, have no real explanation as to why that is. So I've been talking about the beginning of everything, and I've been trying to be very careful that when I say everything, I mean everything we can see in the observable universe. All of the galaxies, all of the stars, all of the gas, all of the dust. That's what I mean by everything. But clearly that's not everything, because the universe is made of everything we can see, plus a whole shed load of dark matter and dark energy. Everything we can see apparently is only 5% of everything that's actually out there. The other 95%, well, that's a bit of a mystery. But, as they say, that's another story. Thank you for listening.
Yes, Dave?